All right. So thank you guys so much for being super patient last week. It was just too crazy and we were traveling and my computer broke and it was a disaster. And of course it happened right when the As You Learn schedule diverged from the website schedule, which was something I was going to fix and then forgot about, but you know how it is. But thanks everybody for being patient and just working through. Again, you can do any lab that you want. You don't have to follow the schedule that I do. I just lecture on based on what your like class lecture, what Dr. Cowan goes off of, so that you guys are sort of learning the same things at the same time. But a lot of these things are so intertwined that it doesn't really matter, especially after we get past the rocks of the seafloor lab. All of this stuff is constantly building on each other, and past the rocks of the seafloor lab, they're really intertwined. So if you have been doing so for example, if you have already done exercise 5, the wave processes in coastal landforms, it's like anywhere I put my phone, it's super loud. And then that's totally fine. You can do tides this week, you can do currents, you can do whatever. Just to say that if you have already done this lab, don't panic. It's totally fine. You're not late by completing it now. Again, I don't grade with which labs you've completed. I just, I grade from the email that I received that says that you have submitted a lab. I go and check out which one it was and go through it. So just to calm anybody's fears, it doesn't matter which lab you do each week. It's just about completing one of the labs. But now I fixed As You Learn and to go with the website. So we should all be like on the same page now. It's just to say that if you have already completed this lab and you're working on tides this week, again, that's totally fine. Or you're working on something else, that's totally fine. The name of the game is just to complete a lab a week. Also, so we're getting close to the end, right? We only have 4 more labs left, and then we have that sort of extra lab in case you have missed something. So the extra lab is on paleobathymetry. However, if the lab that you have missed was exercise 1, the bathymetry lab, I would just go ahead and do exercise 1. Because there's no point in doing a paleobathymetry lab if you haven't learned about bathymetry yet. Right. So if you have missed exercise 1 and you are counting on that extra lab that I talk about in the syllabus and I talked about on the first day that you can complete, just go ahead and finish exercise 1 for that lab because it makes more sense. However, if you've done exercise 1 and let's say you missed, I don't know, exercise 6 or exercise 2, then you have a choice, right? You can either do the paleobathymetry or do your makeup lab on the one that you missed. I just would suggest if exercise 1 was the lab that you've missed, you just go ahead and finish exercise 1. In fact, I would just suggest that you would finish out the labs that are on the website before doing the extra paleobathymetry lab, because the labs that are on the website and on As You Learn are what I'm going to be testing on, right? So labs 1 through 10 are the labs that are going to be on your final exam. Paleobathymetry will not be on your final exam. Okay, so that's just, again, you can do it if you'd like. You can do whatever lab you want. I just don't think it makes much sense to do that one. I think it makes more sense to do it before. Somebody just let out a big yawn, which is great, but just remember to mute because I get distracted super easily. Okay. All right, so today I'm going to be lecturing on wave processes in coastal landforms. So it's a really, really short lecture. This is a very short lab. So hopefully you guys can knock this out pretty soon and then just enjoy the rest of your week. As far as this class goes, you don't have to worry about it anymore. But let's talk about it. So let me, nope. I'm using, instead of PowerPoint, I'm using Google Sheets. No, not Google Sheets, whatever, Google Slides. And let's see how it goes. Okay, so today we're talking about waves. This is literally like a 2 or 3 slide PowerPoint presentation that I'm going to go through the lab a little bit to show you some things. So you all, if you did the tides lab, even if you didn't, or if you did the currents lab, you guys have sort of figured out, right, how surface water and deep surface currents move. You have also figured out about tides and what affects them. And so now we're going to talk about waves in general. Waves are generated by wind and the friction that wind causes on the water surface. So water molecules, actually, just real quick. Okay, never mind. Just making sure I was sharing the right screen. This friction that is caused by wind hitting the surface causes these water molecules to rise and fall in these circular orbits. So if you think about like any time that there's been a really, really windy day and you see these dust tornadoes, or you see like, I don't know, it seems like you see the wind hit the pavement and then dust sort of comes up. That same thing happens with waves. It's just really, really constant. And so it starts this circular pattern of water molecules get hit, they fly up, then they come back down. Then they get hit and they fly up and come back down. Hit, fly up and come back down. So it starts this circular orbit, and those circular orbits form waves. So the bigger your basin, I'll say, the higher your waves can get. So you guys have been to lakes, I'm sure, and you'll notice, right, there's not a lot of wave action, right? There's some for sure, especially on windy days, there's some wave action, but you're never gonna like get, 8-foot, 10-foot waves out there unless something crazy has happened, right? You don't get the type of waves that you get in the ocean. And so waves are definitely impacted by tidal pool, right? That can help with the circular motion, but they are mostly generated by wind. You can see some pretty big waves on like the Great Lakes, right? Any big lake can get a lot of wave action. But we're going to focus just on the ocean because this is oceanography. So the size of waves depends on how fast the wind is flowing, the wind duration, and then the fetch. And the fetch is the open water distance across which the wind blows. So this is the fetch. And let's say that our wind is flowing away from the palm tree. As we make our way all off of the surface and into like deep ocean water, the possibility for really large waves from wind grows. So you guys know probably, or if you don't, that's totally cool. That's why we're in college to learn. But when waves at the surface are building, and they break because they hit some sort of stoppage point, some sort of shallow water. So whenever you're at the beach, let's draw a little beach scenario. So here's my beach, and it drops off like this, whatever. And here will be my water. Let's say that this is my water line here. This is really telling of my shaky hands. And so let's say that we've got wind coming this way, or just waves in general flowing this way into the shore. So you'll notice even in this photo, right, we don't really have a lot of waves out in the ocean, but as they get closer, we have waves developing, right? So surface waves that crash onto beaches are not really dependent on wind. They are a little bit, but they also have the influence of the shore. So what happens is out here, waves can be flowing really, really fast. And then they hit this barrier, basically. So think of if you are roller skating or something like that, or you're ice skating. And you're skating really, really fast on the rink, and suddenly you hit the barrier. What happens? It feels like your body's gonna topple over the barrier, right? Well, the same exact thing happens with waves. It hits this barrier that is the slope, and the energy crashes over and causes the waves to crash over. And so what happens is as the, let's say that let's say red is energy. My energy is going this way. And as I get, or as my energy hits this barrier, instead of being allowed to go forward, the energy suddenly has to go up, right? And so because the energy now has to go up, we start to build waves like that. Okay, so the energy is toppling over itself, basically. So we've got basically calm seas out here and rising waves as we get closer to the shore. So does this scenario make sense to everybody? So in this scenario, wind is a factor, absolutely, but the biggest factor in near shore waves is that you hit this shallow area and the energy has to go somewhere. It can't keep going forward, so it's going to go up and over. Okay? So this little scenario that I'm talking about, let's say it's this green, is living in this area, in the micro ripple area. Okay, as we start getting away into like actual deep ocean, we can still have major waves, right? But instead of being really caused by a barrier or a shallow area, it's caused by wind. So the longer the fetch, which is this distance here, and the greater wind speed, and the longer that the wind has been blowing, the higher our waves can get. So I'm sure you guys have all seen movies or watched that Alaska fishing show, or at least I have, where they're out in, in the Pacific Ocean or in the middle of the Atlantic, wherever else, and there's like massive storms and crazy waves that are going to capsize your boat. Those waves are not caused by a shallow area, right? Those are caused by wind picking up, wind speed, wind duration, and the fact that the wind has been able to travel for a long distance over relatively open seas, right? And cause these major waves. The longer that wind can blow, the longer area that it has for the wind to blow, and the faster it's blowing, it's going to cause more friction and it's going to cause more turbulent seas. Okay, so let's do another arrow and a different color. So the greater the wind speed, the greater the wind duration and the longer the fetch is going to equal, bigger waves. Okay. So you can see here we've got sections of waves, right? We've got micro ripples close to the shore, and then ripples as we start to get away from that continental shelf. Chop, I think you've all heard the expression choppy seas, right? It's a little bit rough, might be pretty dangerous in a kayak or canoe or small boat, but large boats can handle it. And then fully developed seas are when boats are in trouble of being capsized. These are really massive waves, more massive than can be developed near the shore. And they are caused, again, from high wind speeds, wind that's been blowing for a really long time, and really far open water distances. So let's keep talking. I'm going to clear all these. Oh. Okay, so here's an example of sort of that circular movement of the water molecules. So here's at the top, at the surface, that circular movement is larger than at the bottom. And that's because the friction or that wave energy, my waves are going to be green on this slide, or my wind is going to be green on this slide. My wind's blowing this way, right? And wind can really only affect the top of the waves, right? Wind is not going to be down here in the water, right? That's just not how wind works. So the biggest impact is going to be at the top, at the surface. The energy of these waves as well is not moving with the wind, right? The energy is staying in one, in this circular movement in one place relatively. And what's moving through is the water, not the energy. Or sorry, what's moving through, that was opposite, is the circular movement, not the water. And so if you have ever tried to throw a message in a bottle into the ocean, it takes work to get it out to the open sea, right? Because the waves keep carrying it back, but also if you do get it past the waves, it mainly just stays in one place because the water isn't actually moving. It's this circular energy. Right. So if you or if you've ever seen ducks at Duck Pond or wherever else, and there's a little bit of ripple action, those ducks really aren't moving anywhere, right? They're just chilling. What's moving is that circular energy. So it's sort of pushing the wave through. The water isn't actually moving. This circular energy is pushing it up and down. It's just an illusion of it moving. Because of the up and down of the circular energy. So if that is weird to think about, you think about it like this. So if my friction is red, you can think of it like it's pushing the water up here and down here, pushing it up here and down here. So if I keep doing this, if I've got 10 other people beside me and we're all doing this, it's going to create the illusion, oh, like if you do the wave at a stadium, you don't actually move, right? It's just that you have stood up and stood back down. The next people are standing up and standing back down. It creates the illusion of a wave, although nobody is actually moving. So it's the same thing with the water. The water doesn't actually move. It's the energy that just pushes you up and then makes you sit back down. Okay? So in a wave, there are a bunch of different levels. So let me get rid of my cool little drawings. And let's talk about the different parts of a wave. So there's, when talking about waves passing, we can talk about them in frequency, and we can talk about them in periods. So frequency is the number of times a wavelength passes a point in a given time. So how many times a wavelength will pass point A, for example. And a period is the time a wave takes to complete a full wavelength. So more wind speed, longer wind duration, and a longer fetch is going to create shorter periods, right? Because the waves are going to be moving really, really, really fast. If we're having a lazy day, it's going to be longer periods before a wave completes a wavelength. So the greater the period, the greater the wind speed, the greater the wind duration, and most likely the greater fetch as well. So when I'm talking about wavelength, I mean from crest to crest. So the crest is at the very top of the wave. And so I'm measuring from the very top, the apex, to the next apex. This is a full wavelength. You could also hypothetically measure it from trough to trough. So the trough is at the very bottom of the wave. However, the trough is sometimes really hard to spot, and it's way easier to spot the crest of a wave. So that's why we measure from crest to crest. The wave height itself is the difference from the top of the crest to the bottom of the trough. So it's just crest height minus trough height. Let me write that down. When we talk about the wave base, this is at the very bottom of any energy that's associated with the wave. So if you've been to the beach and you've dove underneath the waves, you'll notice, right, when you dive underneath, you might still feel the pull of the waves, but it's definitely not as strong as it is up here, right? That's why you dive under the waves, right? Because you don't want to be blasted in the face by a wave. So you dive under them, the pull or the energy is not as much, and you're getting closer and closer to the wave base. Underneath the wave base, there's no wave action. This area is not affected at all by wind or the friction caused by the wind on the wave surface. Okay, so the wave base is at the bottom of the energy expended or from the friction surface of the ocean. Okay, below here, it's not affected. So this is like way out in the open ocean. If you are close to the shore where humans usually swim, you will not be able to be underneath the wave base. So here's an example of what I mean by that. The wave base is a relatively constant line. It moves depending on, again, wind speed, wind duration, and the openness of, or the fetch. And so if it's, really stormy seas, the wave base is going to move down a little bit, right? Because we've got more wind, more duration, larger waves. And so our wave base is going to move down. But no matter how it moves vertically, it's almost always constant horizontally. So this is what I mean by, if we're in shallow water, you're usually not going to be able to get below the wave base, right? You've got to get pretty far out to get below the wave base. So here you're just in sand, right? Which is impossible to dive into. I guess if you were, yeah, you just can't dive into it. But out here in deep water, you could get below the wave base. Also, waves in shallow water, right, they have this increase in height and decrease in wavelength. So this is what I was talking about that, that energy that's toppling over itself, right? As we hit this barrier that is shallow water, the energy doesn't change, right? It does, it doesn't change its magnitude, but it changes from going horizontally to vertically. So instead of a larger wavelength, what we've got is a shorter wavelength and a larger height. Okay, so this is the wavelength in shallow water. If you bring it over here, you can see, right, that the wavelength is smaller, but our height our amplitude is larger. So this is, again, what we talked about in the beginning about what happens when waves slow down. Their wave period remains constant. So what that means is that, again, the wave period is the time it takes for a wave to cross point A to point B. So that remains constant, but our wave length, again, decreases. This is supposed to be an arrow let's just do that right now. Our wave length decreases, our wave height increases. And we also start to see wave refraction. And so just like when you're canoeing or just looking at a river, you see little V's in the river, that wave refraction is bending around rocks or shallower items, right? So the same thing happens in the ocean. We see wave refraction from the waves bending around bathymetry changes or just depth changes, right? So the ocean is not one singular flat surface, right? It's got bathymetry, it's got elevation, which you guys saw in the first and second labs. So we see that reflected in the waves, just like we see it in rivers. That V that we see in rivers is a refraction around shallower objects. Same thing happens in the ocean. I'm going to double check. I think this is it. And if it is, I want to talk about tsunamis very briefly. I think that's it. Yeah. Okay. So another example of this changing wavelength and wave height is tsunamis. So we've talked about plate tectonics. We know how plate tectonics work. We know that there are plate lines in the middle of the oceans. We know that plate boundaries cause or have earthquakes. They're where a lot of earthquakes are localized or are. We just had this huge earthquake in New Zealand, right? 8.1, which is the largest earthquake that's been recorded since, I think 2000, I could be wrong, but I think like 2009 or 2010 in Peru, which was an 8.0. So it's a huge deal. And it was so big that Hawaii was put on tsunami watch, right? They were all evacuated to the highest point of the islands, and they were put on tsunami watch. So what is a tsunami? It's a large wave, as you might have guessed. But what causes it? So tsunamis can be caused by a lot of things, but the most popular are either debris falls or rock falls into a lake, a dam breaking, or an earthquake in the middle of an ocean or a lake if it's large enough. So if we're talking about rocks sliding into a lake and causing a tsunami, you can just basically think about what happens if you drop a rock or, if you drop a rock into a puddle or into a pond or something like that. It causes massive ripples, right? So imagine 1 trillion rocks falling into a lake, how big a ripple, or at that point a wave, it's going to cause. So it's a massive release of energy from one point that travels very, very quickly. And waves or tsunamis form because, again, of this change in slope. So if I have a rock fall on one side of the lake, that energy travels out really, really fast, just like ripples do. You can think about it like a ripple. And as that energy reaches the other end of the lake, let's say this is a lake now, what happens to that wavelength, right? It gets smaller. The wavelength gets smaller, the wave height gets bigger. And it gets very big because of all of that energy that is expended from the rock fall. And so you can, so that's one way that a tsunami can form. Another way is if a dam breaks, and that's just a release of water, right? So if you've ever knocked over a cup or, I don't know, built a little dam as a kid in a little stream and let it go, it's this massive influx of water. And it's the same sort of deal. Those aren't technically tsunamis, but they work the same way. It's a lot of energy being, and a lot of water being expended at once. It causes these huge waves. Super destructive, very, very fast, incredibly destructive. And then some of the most destructive tsunamis have been from earthquakes. So what we know about fault lines or plate boundaries, let's just say plate boundaries. Let's say that we have a convergent plate boundary. So there's my surface. Here's my boundary. And let's say that we've got an earthquake, and this side, because it's a convergent plate boundary, right? So this side moves up, this side moves down. And this is a little subduction zone, basically. So what happens when this side moves up is it happens in an instant. And it happens so fast, y'all, that like if you were standing on a fault line when an earthquake occurs, especially one that's an 8.1, you would instantly die. Not because of anything falling on you, but because of the energy that's expended in that moment would like turn your insides into jelly. It's like a crazy amount of energy. It's an insane thing to think about. And that, so you can imagine if something is an 8.1 earthquake, which is huge, all of that energy that's expended is basically pushed. So now this side of the plate has been pushed up to here. And you can think of that energy moving in this direction. It's pushing energy that way, and we're usually in deep ocean. So that energy is moving incredibly fast. It's moving really, really fast. And what that means is that the wavelength is very wide. The wave height is barely a ripple. So I don't know if you guys remember the Sumatra earthquake. I think it was in 2001. Maybe you weren't even born. Oh my gosh. But it was this crazy earthquake. Was it 2001 or 2011? I can't remember. It was 20-something-1. And there was reports of scuba divers and fishermen who didn't even register that a tsunami wave had just passed them because they were in such deep water that there was no wave height. There was only wavelength. It was just this wave that was traveling at hundreds of miles per hour, incredibly fast towards, in all directions, really. And so if you were in open ocean, you almost didn't even notice that a tsunami wave had passed. Where the danger happens, right, is when we get to these shallow shallow areas. So as you know, as you get to shallower areas, your wavelength decreases, your wave height increases, and all of that energy that was just that energy that can turn your insides to jelly has not gone anywhere. Now, instead of being a long wave, it has transformed into a high wave, waves that are like tens of meters. So like almost 100 feet, 200 feet waves that are traveling incredibly fast. And then, so as it gets towards the surface, it eventually breaks and topples over. And that's how these huge devastating tsunamis happen. So that's why when New Zealand had this 8.1 earthquake, all the way in Hawaii and even on the west coast of the US, people are on tsunami watch because that energy doesn't really go away anywhere. It has to be absorbed by something, which is usually continents, because it takes so long for it to expend. And so even all the way on that, literally on the other side of the world, when an earthquake happens, there's tsunami watches in the US and on Hawaii because of the danger of these huge waves coming. So that's your waves, right? You've got waves from energy, you've got waves from earthquakes, you've got waves from wind, and then you've got waves from all three of those things, right? So when you are, again, just a quick recap, when you are at the beach, those waves that you see are mostly a change in energy, right? From, or I guess a change in the concentration of energy. So instead of going this way, your energy is building up. Huge waves that you see out in the deep ocean are wind duration, wind speed, and the fetch. And then tsunami waves, which you hopefully never see, are usually from earthquakes, which is, again, a type of energy. And then just to say also, of course, waves closer to the shore also depend a lot on wind, right? So if there's a crazy storm out in the ocean, usually the waves closer to the shore are really crazy. There's a lot of rip currents, stuff like that. So definitely it's also dependent on wind. I just mean in general, waves closer to the shore have a more, the energy is more impactful than out here where the wind is really the name of the game. Okay, so that is the lecture. Let's talk about the lab very quickly. Again, it's a super short lab. It's already done right here. But I wanted to point out some resources for you all. So here is this link for completing the table 5.1. It should just be view only. So when you click on this, it'll take you here. For me, I'm allowed to edit it because I'm the author. For you, it might just be view only. So what you need to do is either download it directly to your computer, or you can make a copy that you then can edit. All right, either way works. And then you can download it and print it off. Same goes for down here. You need to ID these structures, which you'll learn about. So if you want a bigger view of these structures, you can just click on this link and you got them right here. Okay. So just quickly, I want to talk about this refraction. So this is what I meant by wave refraction when I talked about waves bending around bathymetric changes. So this is a little bit of a headland. You could, if it's a small peninsula, right? And so these headlands usually they carry out into the sea a little bit, and you can see, right, how these waves have refracted around this area. And so if you remember from the bathymetry lab, and looking at isobaths, you can almost think of these lines, even though they are wave crests, you can imagine them as isobaths. And so remember, when I have something that is Ving up, right, it is Ving towards a ridge, a shallower area, and things that are Ving down in this instance are Ving towards a canyon or a deeper area. So these wave crests are Ving around this shallower area here, right? So this is what I mean by everything is connecting, right? You can use what you know from the bathymetry lab to help you with this wave refraction. here's an example in real life, right? We've got this little bit of headland jetting out, and you can see how these waves are Ving around it, right? They're starting out like this, they're crashing this way. And as it goes around, here, let me actually draw. They start crashing this way, right? This is the wave crest here. And as it V's around this little headland, the waves change their crest, right? Can you guys all see? So now they're crashing this way. And then in fact, as it gets farther away from the headland, we return back to this sort of more, I guess I'll say normal line that it was over here, right? So we've got a little bit of a refraction here, and then it returns back to normal. Can you all see that? You can almost see it over here a little bit too. These wave crests here, they're refracting around this little headland, so it changes again. So our wave crest, for the most part, is heading this way, but it just happens to get refracted around these not jetties, little headlands, and changes the refraction slightly to this way. Does anybody have any questions about that? Can anybody not see what I'm talking about? Okay, awesome. That should be it. If you have any questions, of course, I'm here. I have a computer now, so I'll be here for office hours, and also other times if you need to meet, feel free. Does anybody have any questions about the lab now? Feel free to ask. Okay, all right. Awesome. That's it. I hope you guys have a good week. I'll see you in office hours or whenever else if you need help. And I'll talk to you later.
Thank you. Have a good one.
See ya.
Thank you.